Welcome back to our second segment. We're still exploring resistors in series in a series circuit. Safe to say that we also now are familiar with how we exactly measure, the resistance of a resistor in a simple circuit. We need to have the voltage across that resistor, as well as having an awareness in terms of how much current passes through that resistor, which is the amount of charge that passes through that component per unit time, right? So now to measure the total resistance, this total resistance will be our effective resistance in the circuit, okay? Then we need to have an indication of the terminal potential difference. This is the voltage across the battery when there is current in the circuit. And we also need to know how much current passes through the battery. And then this is the total current, right? That's the total current in the circuit, because all the current will pass through the battery. So this is total resistance. We would abbreviate it as R subscript T. Okay, so if we have the terminal potential difference, which is the total voltage again, we have also the total current, we are able to determine how much total resistance we have in a given circuit. Right, now let's use a simulation to kind of look into how exactly we measure terminal potential difference as well as, the total current in a simple circuit. Okay, so if we go to our simulation, okay, we have something of this sort. Okay, there is no current in the circuit because we are saying that in this circuit, the circuit is broken or the switch is open. But the moment we close the switch, there is current that is registered in the circuit of 0.9 amperes. Okay, so if we are to determine the magnitude of terminal potential difference, we would actually go to the battery and actually measure the potential difference across the battery. In this case, it's 9 volts. Now, the resistance in the circuit is a result of us understanding what's the terminal potential difference as well as what's the total current passing through the battery. So if we can also use, the value of potential difference across the resistor, it will give us the same thing, because this is the only resistor in the circuit, so it gives us the total resistance. So the voltage across the resistor is actually equals to the voltage across the source. Okay, so that's our value of terminal potential difference, while the current is not 0.9. But this is only possible if the circuit is complete. But if we decide to break the circuit, there is a potential difference of 9 volts, which is actually the EMF, which is also equal to the terminal potential difference. What does that tell us? It tells us that this battery does not offer any resistance in the circuit. So if we got the current reading and the terminal potential difference reading, we are able to determine the total resistance in this circuit. Right. Okay. Going back to our slide. Now, here is a scenario. If the total voltage in the circuit was 9 volts, okay, and then the total current that was registered is also 0.9 amperes, then obviously the 10 ohms comes from R is equals to total voltage, okay, divided by total current. So this is total resistance, okay? That's how we get the 10. So it's 9 over 0.9, which gives us the 10 ohms, right? Okay, now to measure the resistance, this is what we are saying. You must measure the potential difference across the component. Now, in this case, when we talk about the component, we actually talking about the resistor itself. It could be a light bulb or whatever the case may be. So if we measured the total resistance by measuring the terminal potential difference, this gives us an indication of the total resistance in the circuit, provided we know how much current passes through the battery. But now, if we are to measure or determine the resistance of a component, the potential difference resistance must be measured across the resistor itself. And we must know how much current passes through that resistor. Then we can get the resistance of that particular component or resistor. Okay? Now, so the current passing through the resistor is also very important, because now, let's say we talk about resistor 1 for argument's sake. So resistance of resistor 1 is equals to voltage across resistor 1 divided by the current that passes through resistor 1. So take note, we're still using the very same mathematical equation to determine the resistance, right? Okay. Now, we can do that using a simulation and get a sense of what exactly we are talking about. Okay. Now, if we are to measure the voltage across the resistor, we'll obviously take the terminals across the resistor. It gives us 9 volts, and then there is a current of 0.9 amperes passing through the very same resistor. So we can, if we say this resistor is R1, then we can determine the value of R1 using the voltage across R1 and the current passing through R1. Right? Simple, straightforward. There's nothing, rocket science about that. Okay. So this is what basically we have verified. Okay. Right. Now, we want to measure resistance. Okay. This is what we are saying. There's only one, if there's only one resistor in a circuit, as we have seen in the previous example, the resistance of the resistor is equal to the total resistance of the circuit. So in the case of R1, being the only resistor in the circuit, so if we go back to the table of results, so the total resistance is a result of R1 being the only resistor in the circuit. Okay, so in other words, resistance of R1 equals to R total if and only if R1 is the only resistor in the circuit. So we simply trying to say as long as there is a single resistor, that resistor is what accounts for the total resistance in the entire circuit. Right. Okay. Now, we are clear with that. And then we are saying that the other assumption that we are working on is that the ammeter, which is always connected in series, and the conducting wires, okay, have negligible resistance. Okay, let's try and unpack that term. If we assume that the conducting wires and the ammeters that are connected in series are actually have got negligible resistance, it says to us that the resistance in the total circuit, is offered by other component except for the conducting wires and the ammeters. So all the current will pass through the ammeter. So the ammeter in itself, as well as the conductor, they do not provide any opposition to the flow of charge. That's the main thing about it when we say it's negligible. So the term negligible resistance will be used, in many of the circuits that we shall try and explore as we go along. Right? Okay? And then here's a thinking question about measuring resistance. What happens to the total resistance? Okay, we're talking about R total. Take note of that, of the circuit when more resistors are connected in series. This is a thinking question. Okay, now here's a scenario. Instead of having just one resistor, we'll add another resistor. Whether it's identical or not, it doesn't matter. Now let's go to the simulation and try to explore that as well. Okay, so that's our circuit. Okay, let's add another resistor to this circuit and see exactly what happens when we add more resistors in series. Okay, right. Okay, just to create more space for that. Okay, so that's our one resistor. Okay, we'll add another one. Okay, of same resistance, just to make life much easier for us. Okay, right. So there are two resistors there that have been added. We've added one. There are two identical resistors. R1 is 10 ohms. R2 is another 10 ohms. Okay. Now the question that we asked: what happens to the total resistance when we increase the number of resistors in series? Okay. But remember, what is resistance? Resistance is the opposition to the flow. Okay. So if we are to demonstrate that, let's use the conventional current just to show what is happening. The amount of charge that passes through our ammeter has is actually been halved. It was 0.9, now it's 0.45, which is half the original, okay? It means that if we add more resistors in series, what does that tell us? The opposition to the flow of charge increases. That's effectively the resistance of the circuit. So if the first one is R1 and the second one is R2, the total resistance has increased. That's why, which explains to us that the value of current is also decreased, okay? Now, if we realize that there is a decrease, so if resistor 1, the voltage across resistor 1 is something that we also need to measure, okay? But the current that passes through both of them, it's something else. If we are to measure the voltage, okay? So the voltage in this case, there is a voltage, okay? The voltage is 9 volts. That's the terminal potential difference across the source, okay? Now, in this case, this one is going to be 4.5. What if, for argument's sake, we change the resistance of this one to make it, say, for argument's sake, half that one and see what happens? Okay, if we make it half, it means it's going to be 5 ohms, right? So if it's 5 ohms, okay, this is the voltage across R1. So R1 is 10 ohms, R2 is 5 ohms. Now, the total current is decreased from 0.9 to 0.6 amperes. But I just want you to check something very important. Our terminal potential difference, which is the total voltage, is 9. Okay, look at the voltage across R1, okay, which is 6 volts, and then voltage across R2, it's 3 volts. Okay, if you say 6 plus 3, it should give you that 9. Okay, it should give you the 9, right? So if we go back, okay, resistor 1, the total resistance is 15 ohms, okay? The resistance for R1 is 10 ohms, right? Resistance for R2 is 5 ohms. This is what we realized, okay? That's the total current. Voltage across R1, it's 6 volts, okay? Across R2, we measured it to be 3. Now, the total current, we can determine the current that passes through each one of those, okay? As you can see, there is a single path for current to flow. It means the same amount of current passes through R1, through R2, as well as through the battery, which is the source. So there's a constant amount of current passing through. So we still have a 0.6 there and 0.6, okay? Now, if you realize that if we add more resistors in series, the total resistance has increased, which has decreased also the total current in the circuit. That's the main idea that we wanted to actually explore, right? Okay? Now, okay, what happens to the resistance of resistor 1 when connected in series with a second different resistor? We realize that the resistance doesn't change, okay, of R1, because if we go back to our simulation, if we calculate the resistance of R1, we've got 6 volts versus the 0.6 amperes, it will still give us the same, 10 ohms, okay? But also, if we calculate, we measure the voltage across R2, which is 3 volts, divided by the total current, this will give us 5 ohms, okay? So, which is exactly the value. But if we also measure across R1, it gives us an indication that also it's 6 volts. But there's something very interesting about the total voltage in this circuit, which is something that we want to arrive at. Okay, so this is a big question. What happens to the resistance of resistors R1 when connected in series with a second resistor? Okay, right. So we have measured the 6 volts and confirmed that, which is fine, right? Now, for R2, we also realized that this is 3, okay, which gives us the total of 9. The same amount of current passes through each one of them, including the battery, okay? And then this was half the resistance of R1, okay? Okay, that's the main idea, right? Okay, so we've confirmed these results. Also, measuring is a very, very important skill in the scientific process, and also how then we use that data to analyze, okay? we need to arrive to some sort of a logical conclusion. Now, in terms of measuring resistance, what conclusion can you make about the relationship between the total resistance in a circuit and the resistance of the two resistors? It was straightforward. We had the 15. So this 15, which is the R total, actually comes from the sum of R1 and R2. So we can immediately project from this that the more resistors we add in series, the greater the effective resistance of the circuit, right? Okay. So this is actually the main point about how we determine resistance in a series circuit. So the more resistors connected in series, the greater the equivalent resistance. So if we talk about equivalent resistance, we're talking about total resistance. Sometimes we would refer to it as the effective resistance of the circuit. Right. So that's the main idea. So in as far as measuring, we need to determine the amount of voltage across a component, okay, so that we are able to also know how much current passes through it, and then we can use the mathematical equation R is equals to V over I. But the main idea about the simulation that we just explored is that as long as we continue to add multiple resistors in series, the effective resistance of the circuit will increase. Let's take a short break for now.